6.1, we're going to do law of sines, and it really has the same purpose as law of cosines. It just works for different information. So there's a couple cases where law of cosines works and law of sines works on other information. But unlike last semester, law of sines works for any triangle, right triangle or not. So that makes it a little more versatile in moving forward. So super easy formula to memorize. These are the law of sines, and it's really just the same thing, just reciprocal. I tend, and you can do what you want, this is just more my preference, I tend to use these top ones if I'm finding an angle measure, and I tend to use these down here if I want a side length. But it really doesn't matter. Sometimes it just saves you like one step of work if you do it that way. So law of sine says if you took the length of A and divided it by the sine of angle A, it should be equal to the length of B over the sine of angle B, and or equal to the length of C over the sine of C. So this proportion. All right, so when law of sines works, so just like law of cosines, we expect you to know when you can use it. You can use it anytime you have two angles in one side. So that could be angle side angle or angle angle side. And we'll talk about what the difference between those two are. And then sometimes side side angle. Unfortunately, side side angle is what makes law of sines more complicated than law of cosines. Today we're not going to get into the side-side angle case. It's called the ambiguous case, but we're going to look at the easier stuff just so we have it checked off. Because a lot of law of sines just works like a lot of law of cosines work for us. Okay, so when I say angle side angle, what I mean is in a triangle, I know an angle, I know a second angle, I'm just making up numbers of course, and then the side length I know is in between those. It's an included side. Just like the S is trapped between the A's, the side length that I know has to be that one. Angle side has the same information, also two angles in one side, but which side you know could be different, or would be different. So over here for angle side, here's an angle, and I don't know this side. Because if I knew this side, it would be this case and not the other case. So I either know this length over here or I know this length over here. Because this would be angle side or angle side. And then so that's what works. So something like side, as much as you want to use law of sines, it's just not going to help you. Look at the formula. If I plugged in a length for A, a length for B, and a length for C, I'm always going to have two, I could ignore part of the formula, but I would still have two unknowns. I wouldn't know angle A and I wouldn't know angle B. You've got to get it down to a single unknown so that we can solve for it. So that's why side doesn't work. Side angle side as well. All right, so the reason that the side angle gets complicated, if you remember back to your geometry days and if you've been reviewing for the ACT anytime recently, in geometry you learned some triangle congruent shortcuts, and there's 5 of them. Side, side angle side, angle side angle, angle side, and hypotenuse leg, which means those guarantee a unique triangle. So, of course, if we had unlimited time, I could pass out a bunch of like toothpicks, give you all the same 3 lengths, and ask you to make a triangle, and you would all make the same triangle. If I gave you, told you to make 2 angles, and then outside of those 2 angles, use a certain side length, you would all make the same triangle. But you remember that stuff from geometry, right? Or it sounds familiar at least. Side angle wasn't in that list because side angle doesn't guarantee you one triangle. You might have no triangles with those numbers, you might have 1, and you could even have 2. So that's why we have to spend a little more time with law of sines than we did with law of cosines. But we can practice the easy ones first. And just to kind of start off, here's an example of someone working and finding a side length. You can see they plugged in 3 numbers. 10 is opposite 48. So they said the sine of 48 divided by 10. And then 55 is opposite x. So they said the sine of 55 equals x. And they cross multiplied, put it in their calculator. Calculator would need to be in degree mode. Hit enter, and it tells you how big that side x is. Pretty easy to solve. Plug in the 3 things you have, solve for the 1 thing that you want. Okay, over here, they're solving for an angle. So same thing, they plugged in 3 things that they knew. They had 1 thing they didn't know. So cross multiply, get it down to sine of x equals, and to switch it from sine of x equals to x equals, you would do inverse sine. Now notice, law of cosines had cosines in the formula. Law of sines only has sines in the formula. I know that sounds obvious, but sometimes people sneak a cosine into the law of sines or vice versa. Okay, so these 2 are both going to be the ones that just work. There's not going to be anything tricky about these. We just need to make sure that we can apply the formula. So if I gave you the size of angle A, the size of angle B, and the length of A, you should be able to find the length of B. So I actually want you to take a couple minutes, look at that formula on the front page, throw in those 3 numbers, and see how you would go about solving for B and see what you get. Okay, so just at quick glance, I don't have the answer memorized from last period, but what would be realistic without doing any work is I can see angle B is bigger than angle A, and side A is 10, so that means side B should be a little bit bigger than 10, right? That would be a realistic answer. Okay, so what your work should look like is something like B divided by the sine of B is equal to A over the sine of A, or reciprocals on both sides if you'd rather. From here you can cross multiply, or you could just multiply both sides by the sine of 55 degrees. And again, assuming you're in degree mode, this is not the tricky case, not the ambiguous case, so we don't have to second guess our work or the calculator's answer. Looks like it comes out to be 11.023. Okay, so not bad at all. All right, number 2's got a little bit of a twist to it, so figure out your mistake that you may have made in number 1, and then see if you know how to proceed in number 2. Okay, so for this one, if you were trying to find for the length of b, even with just a tiny bit of practice we've had, you know that it has to go over the sine of b. Okay, and then you can set that equal to a over the sine of a. The problem is I don't know the length of a. Or you could set it at c over the sine of c. And then the problem is I don't know angle c. And I can only have one variable if I expect to solve for this. So there's not enough information, at least not to do a bunch more work, to find side A, but side C shouldn't be a problem because you have the other two. They should all add up to 180. So if you subtracted away angle A and angle B, you should know angle C was 94. With little effort there. So I chose to set it to c over the sine of c. Cross multiply, or just undo the dividing of sine of 36 by timesing by the sine of 36. And I'm getting about 74.831. Okay, and then short of finding everything else, which I guess would just be side A, you could at least make sure, you know, B is smaller than A, so side B should be smaller. Well, I don't have that one. B is much smaller than C, so side B should be smaller than C. So I can see that that's true at least. So for 2 of the 3 cases, it's not a big deal. I mean, obviously you need to practice it a couple times, but you basically throw in the numbers, solve for what you want, and if you don't have the exact numbers, then it's usually not too much work to find what you need. Okay, so we're not going to go over the ambiguous case today, but I do want you to see like what the process is going to look like. So we're going to just kind of emphasize how much there is to it and what we'll focus on next time, and then we'll finish with the new area formula on the bottom of the back page. So the ambiguous case, side angle, because this doesn't guarantee one triangle, what we have to do is we have to really analyze this angle. if this angle given to you is an obtuse angle, then we get one of two cases. We have to check for a couple things. But if that angle given to you in side-side angle is a right angle, well, then that's kind of a boring case, because you've got a right triangle. You can use all the stuff from last semester. And then if the angle given to you is an acute angle, depending on the numbers, you may not have a triangle. Those values may not be able to connect. Those values might connect perfectly where you get one unique triangle, or you could even get it to where you get one or two triangles. And so it's not that it's hard, it's a lot of information at once. So unfortunately, it just comes with the law of sines. But we'll practice a bunch on trying to figure out how many triangles we can make, whether it's 0, 1, or 2, after we talk about that next time. And then we'll talk about how to find angle B if there's more than one possibility for angle B next time. But to finish off just our introduction, we've got one more formula for area of a triangle that you will be quizzed on this section and part of your test when we get to that. So the other formula that we gave you, Heron's formula, is great if you have side, side, side. These formulas I'm about to give to you are more useful if you have side, angle, side. So 2 weeks ago, the only area formula I would have expected you to know is area is 1/2 base times height. Well, let's sketch I'm going to give you these formulas on the quiz and on the test, but I want you to have an idea of where they came from. So here's some generic triangle ABC, and you know, any side can be the base. I know most people like to make it this bottom one, but it doesn't have to be. Let's say this is A, B, B, C, C. Okay, so another way to say 1/2 base times height is to say 1/2, and I'm going to call the base this time A. And if I was to do that, then that makes this the height. And if we had numbers, we could kind of seek it out and find a numerical answer. But another way to solve for this height, if I was to look from this angle B, I could say, well, the sine of B is equal to opposite over hypotenuse. I'm allowed to do that because I'm looking at a right triangle. And so height, opposite over hypotenuse. So height, when A is the base, would be C times the sine of B. So the height in that scenario would be C times the sine of B. So it's still 1/2 base times height. It's just that I'm saying, hey, the base is A, and from a SOHCAHTOA equation, the height would be C times the sine of B. Okay, well, I could rotate my triangle if I wanted to. A doesn't have to be the base. B could be the base, or C could be the base. That's just going to change what the height would be. So we're not going to sketch all of them out because there's quite a bit of pattern recognition here. But one of them could be 1/2 AC times the sine of B. One could be 1/2 BC times the sine of A. And so what do you think the rest of this one would be? Well, what combination have we not used? We've used AC and we've used BC, so we didn't use, oops, yeah, I used C twice. We didn't use AB, right? And that would be, if I had these two links, the angle that would have to be in between those, because side angle side, would have to be C. So it's just a different take on 1/2 base times height. It's just that somebody went out there and said, okay, I'm going to do a SOHCAHTOA equation for you for the height. But these are a good way to think of area when you're given that information. So again, not anything that you need to memorize. I would suspect, though, if they threw this on the ACT, they would not give you those formulas, so you might take that initiative.